Hello everyone. My name is Joe Arcelli. I'm going to share my screen 1 second. And the idea today is that we will do what I think we are calling a lunch and learn session. I am going to present who I am, a particular acoustic solution called Actran. I'm working for the company that develops this software. And a particular use case for this solution. So just radiation of a vibrating structure. I want to have it be a little bit interactive, so feel free to interrupt me if you have some questions for me. That is totally fine. We can lose 5 minutes to talk about something you want to talk about. Yeah. So the idea today is I'll spend just 5 minutes introducing myself, the software, how it works at a very high level. Then I will talk about some of the things it is able to do, some of the key features and things that differentiate it and make it very powerful. And then I will show the software itself just on my laptop with a little demo case of radiating gearbox. And yeah, how it could be put underneath a vehicle to see how the noise propagates around the outside of a vehicle. So maybe without any further ado, first a little bit about myself. My name is Joe Arcelli. I'm working with Hexagon Manufacturing Intelligence, specifically the team that makes the acoustic solution Actran for the past 6.5 years now. I did undergraduate in mechanical engineering and master in acoustics and fluid dynamics. Besides work, I have a personal life as well. I'm from New York originally, but living now in Europe for more than 7 years in Belgium. I love animals, have a little pet dog right here. Her name is Stanky. And last year it was the marriage of my brother, so I just put that picture in as well. Okay, so that's me. What about the tool I want to talk to you about today? Actran. So Actran is a finite element-based acoustic solution. It does vibroacoustics problems, so ones where you have a vibrating structure, as well as aeroacoustic problems, where we might convert CFD data to acoustic sources. It's scalable, meaning that we run large industrial-sized jobs on our HPC and cluster configurations. It's used for various different industries: aerospace, automotive, hi-fi equipment and manufacturing goods, and all the normal stuff, I would say. We have many different validation cases proving that the results are accurate and verifiable, and it's supported by a large team of experts and engineers, myself being one of them. Okay, so Actran can solve a lot of different acoustic problems, but today I want to just focus on one particular type of problem: acoustic radiation. This is a sort of problem where you have structure dynamics, a vibrating structure, and the structure vibration can be computed via some kind of structure solution, so be it finite element solution or multi-body simulation solution, or measured in a lab with different accelerometers. Then we create an acoustic finite element mesh surrounding the structure with some kind of non-reflecting condition or reflecting condition, depending on what we have. We use a particular boundary condition called a boundary condition mesh. We call it BC mesh, which just loads and converts the structure vibrations into an acoustic excitation. And then we propagate that excitation into the finite element space we have created. Like I say, your structure dynamics can come from finite element solutions, multi-body dynamic solutions, measurement, maybe a combination of some electromagnetic forces and structure that we load in Actran. And we can solve problems either in physical coordinates, meaning is there a question or someone just joined?
Someone just joined.
Okay, I go on then. So we can solve things in physical coordinates or in modal coordinates. This is, I would say, a standard sort of way to go in dynamic analysis. The way we recommend building up these kind of acoustic radiation analyses is to progressively add complexity. I think it's a lot easier to start simple and then add on every bit of the physics you want to model rather than starting with the full set of physics and then going backwards to figure out what is working and what not. So typically the way we work is we start by modeling structure vibrating in free field. By that, I mean a completely open space or like an anechoic room. And even with this simple simulation, you already get interesting outputs like sound pressure level at locations in any point in space around the vibrating structure, what its radiated power will be, how efficiently different parts of the structure radiate. Then, as we build complexity, maybe we can think about some kind of acoustic treatments and absorption materials that we might want to add. This can be some kind of foams or damping materials that we want to add to a vibrating component. It can be absorbing materials in a room or a space to reduce the reverberation time. There's many different things we can model in Actran, but that would typically be a level 2 once we've just simulated the bare radiation. And then level 3 would be what I call complex propagation, where we take simple, maybe powertrain, gearbox, loudspeaker that is just on its own, and then put it into a realistic environment. So connect it to pieces in a vehicle, put it where it will actually be installed, and so on. Okay, any questions about anything I say so far? If no questions, I want to talk about some of the, let's say, killer features that we have in Actran that make it super efficient for modeling acoustic radiation. I won't spend too much time here because I think it's more interesting to see the demo case than for me to just brag about the different capabilities the software has. But in a nutshell, we'll be talking about things that make the software easy to use, complete in that it can handle all sorts of different problems, how we maximize the performance to be able to scale to any size problem, how the software can be automated in order to set up a lot of the analysis for you, and some optimization points as well. So for ease of use, I would say one of the big selling points for an acoustic solution is it has to be able to couple with other softwares easily. The vibrations that will be propagated by Actran are typically solved in other finite element or multi-body dynamic tools. They can be measured as well, but we couple with, I would say, most finite element solvers, Abaqus, Nastran, Romax, Atoms, other ones as well. If you are using already a particular structure solution, I would refer you just to check out our guide or send me a little message and I can say, yes, we're supporting your vibrations from there, and we can tell you how those vibrations will radiate, or how we would go about converting that type of vibration to something that we can read in the software. Okay. Besides the coupling with previous solutions, we have to have a robust library of meshing tools for creating acoustic meshes. Luckily, creating an acoustic mesh is a lot easier than creating a structure mesh. So we focus our efforts on specific tools that will do things that make it easy to create an acoustic mesh. By that, I mean we'll have some specific tools for automatically detecting and filling holes in structure meshes, creating shrink wraps that completely go around either the inside or outside of structure mesh you load into the software. And then, let's say, automated tools that create adaptive acoustic meshes for modeling the near and far field. By that, I mean that we have some components and tools that will create finer meshes for higher frequencies that come closer to your structure, and coarser meshes for solving lower frequencies that are also bigger to allow, let's say, one complete wavelength between the structure and the end of the finite element mesh. We also support a lot of different post-processing. So if you're interested in these so-called Campbell diagrams or order analysis of a vibrating structure, we have that. You can plot things like frequency response functions at a particular microphone in narrow band, third octave band, directivity plots, propagation maps, let's say panel analysis where we compare the different power radiated by different panels in a complete vibrating structure. So we have a lot of different post-processing tools available to you to make your lives easier and to get a deep understanding of the physics you're modeling, including some ISO, say, indicators, things that will tell you what is the experimental radiated power or what is the pass-by noise of a vehicle. Okay, on the completeness side of things, we want to make sure that Actran can do a lot of different problems. So for just the acoustic radiation, we make sure that we have engine, gearbox, any type of powertrain radiation supported in free field, with a floor, with encapsulation, without. We also make sure that we support e-machines as electrification takes off. We have as well support for pass-by noise, the noise a vehicle would make as it goes by a microphone, exhaust noise, tire noise, noise from loudspeakers. There's really, I would say, a wide range of applications you can use to compute the acoustic radiation. We just need as input some kind of structure vibration. On the performance side of things, we have a couple different analyses that can really help you tune something you set up in Actran to get as good performance and industrial models running as fast as possible. One of these is so-called green analysis, where we limit the number of output results we want or are interested in to a selection of microphones, and we compute noise transfer functions in a first step to then be able to use any type of input vibration to compute what the corresponding noise level at the input points would be. This is just a type of analysis that lets you really supercharge your speed for many different RPMs or configurations of powertrain components particularly, once you're happy with an initial Actran simulation. I spoke about this one already, but we have adaptive mesh components in Actran that will create coarse meshes for you at low frequencies and fine meshes for you at higher frequencies. This really helps you speed up the overall computation while you don't have to invest any work. It's the solver itself that creates this kind of stuff for you. On the automation side of things, we're also pushing for what we call workflow tools. These are vertical solutions that are meant to not require super expertise in the software Actran to use. The idea is that you can take some measurements or inputs from previous simulations that you've already computed, and it will do a lot of result recombination and post-processing automatically for you. You provide a few inputs and a few results, and you don't have to do any complicated post-processing. You just get the most significant and important output indicators displayed automatically. We have one of these for Passby noise, EM noise, damping pads. There are some other ones as well. And each one comes with a little demo that's available online for, let's say, Hexagon customers. You can download the demo and give it a try if it's one that's interesting for you. Okay. Any questions about any of those features? I went through it a little fast, but I think it's more interesting to see the demonstration. All right. For the demonstration, I'm going to jump out of PowerPoint for a minute and just go to the software. So here I have the current release of Actran 2025.1. This is what the GUI looks like. You have this ribbon up at the top with all the different steps kind of arranged in a story kind of way for setting up an analysis. You start building the mesh, you build the analysis, you run it, you take a look at the results, and would go from there. In the center, you have this render window, which if I create just a little mesh like this, you have, I would say, quite similar to many CAE tools, display of what we are looking at. I can change some things with the visualization. The driving takes a little bit getting used to. Every tool is a little bit different, but I would say no problem for engineers familiar with other CAE tools. And just here on the right, we have these trees. They're hierarchical structures containing the different meshes, the different materials that we have defined. In this case, I haven't defined any materials yet. I could maybe create an analysis and then create here a fluid material or something like that. And yeah, there's another set of trees here with the analysis containing its components, connectors, boundary conditions, and what sort of results you would like to request. Okay. Any questions about the GUI or what I am looking at and showing right now? If not, I'm going to just show this demo model. So I will import it already finished, but I will build it in front of you too. I think that's, I would say, part of the fun. Oops, I picked the wrong one. So this is the first bit of this demo we want to take a look at. It's acoustic radiation of a simple gearbox. So we have two meshes here. One is a shrink wrap of the gearbox. The other contains some stuff for outputs. So we would request a map on this disk and results on this set of microphones. So the analysis is already built up here, but let me show maybe how I would build this from scratch. So I might start with structure mesh. So this particular structure mesh was solved, the structure dynamics were solved with Nastran. I can visualize the displacement and maybe let's look at the deformation as well. Let's see. Okay, that's a little bit too much. But yeah, for different frequencies, I can see that, okay, this gearbox is radiating. Let's go here. So I have results between 400 and 600 hertz in this case. I can animate it. And with this structure result, I want to create an acoustic analysis. So how would I do that? The first step is to create a shrink wrap of this structure. So the way I would do that is with some meshing tools here. I'm not going to do it now, but you could use this fill holes tool to fill these holes, and then this exterior shrink wrap tool to create a shrink wrap around it. For now, I'm just going to grab this coupling surface. So I just dragged and dropped another mesh here. I'll hide the structure and show only this shrink wrap. All right, I'll make it blue. All right, let's define the analysis. To do that, I can create this direct frequency response analysis, which solves a discrete set of frequencies. In this case, I want to
Joseph, if I
solve.
may interrupt you quickly,
Yeah, please.
how important is the quality of the shrink wrap mesh?
Great question. So typically, because the acoustic wavelength is much larger than the structure wavelength, you only need to follow really as close to the details of the structure as the acoustic wavelength or half wavelength, let's say. So in this case, because the acoustic wavelength is much larger than the geometric details of the structure, we can get away with something that is kind of coarse like this. Typically, I would say at a maximum, don't have the shrink wrap be factor 2 more coarse than the underlying structure.
Okay, thank you.
So I was just going to, where do I have my structure results? Structure.nff. Where is NFF? So what I'm going to do here is just refer to the frequencies that we have available in the structure mesh. So we saw it was from 400 to 600 hertz. I'm going to create an exterior acoustic component. I will create a domain for this. I will call it, yeah, let's just call it shrink wrap. So this exterior acoustic component, it's the auto adaptive one I spoke about. The way it works is it creates coarse meshes at low frequencies and finer meshes at higher frequencies. We, as of a release or two ago, have an automatic setup, but I'm going to do a manual setup. So we're going to say that we want to create exterior acoustic component made of air. I want to compute the radiated power. We will have a thickness of 10 centimeters, 8 elements here per wavelength. And I will use this infinite element type boundary condition. There's two boundary conditions here. Both are non-reflecting boundaries, but I'm going to use this one. The component or the connectors, we should define a connector just on this shrink wrap to define now this BC mesh, which is going to excite the model and convert the structure vibrations to equivalent acoustic velocity and pressure. So the mesh format is going to be same as before. The BC type is going to be a displacement. We looked at the results and they were displacement, but it could be acceleration or velocity or modes plus modal participation factor. And we can define a tolerance here. I'll just take the default parameters. And finally, we want to have, let's see, I think it was this. Yeah, a mesh here, which is just going to define a map. So I'm going to request a field map. That's the sort of map where we don't have nodes that are computed in the simulation, but generic nodes. Map.nff. And with that, I think the analysis is ready to go. So let's try to run it and we'll see if I set it up correctly or if I forgot something. So I just launch it here from the GUI, but of course you can launch it on your HPC environments as well, or from a command line. It's really how you prefer. And while that's running, maybe I'll already show a little bit of the post-processing. So what we can do is take a look at this free field PLT file. So this is the result we should achieve eventually. And we can look at these PLT files in the PLT viewer tool. So that's this tool that we use for curve tracing and things like this. And we have here some global parameters. So things like what is the radiated power through the entire exterior acoustic mesh. We can plot what is the, so here, radiated power. Format this as we like. Copy a snapshot or export the image to go right into a PowerPoint or something like that. And in addition to the global parameters, we have some local parameters. So there were a bunch of microphones, which I forgot to define in the analysis I just set up, but maybe I can grab the original. Yeah, so we had, it looks like 360 microphones all around this particular gearbox. We can look at a single one. What is the SPL? What is the pressure at that microphone? Or what we can do is we can create this reverse set to have the directivity at, let's say, a given frequency. So at 600 Hertz, we can plot again the SPL and then use this polar type chart to see what would the directivity of the gearbox be at this particular frequency. Let's say with 0 being up here, 180 being down here. Let's see how the run is going here. Okay, so the run finished. When you launch a job, you get this kind of run log that tells you what the simulation is doing at each step. It will throw you an error message if something is set up incorrectly. Usually they're pretty clear and can help you debug yourself, but if you get stuck, don't be shy to write us a mail at support. Okay, and I see that we wrote this map that we requested, so I will see about that map. Okay, let's hide everything and show only this map. So here we can take a look at the real or SPL pressure at different frequencies. So we see here at 600 hertz, the bottom part is radiating less efficiently, I would say, than this top part, which we saw a little bit in this directivity plot. We have a higher SPL on the top than at the bottom. And it might be a little bit surprising because we see that the absolute level here at the bottom is higher, but it is radiating less efficiently. Let's see. I have maybe one last thing to show with this demo, which is how we could take this simple structure in free field, so just kind of sitting on its own in non-reflecting boundary, to an installed location. I'm not going to set this one up, but the setup you can see is largely the same. We used the same component, this exterior acoustic, to make the mesh for us automatically. The BC mesh, again, is just on the gearbox. The only difference now is that we have a complete shrink wrap of an entire vehicle here that we would propagate the noise around. And with that, we could compute things like the pressure on windshields for loading the inside. We could see the pass-by noise of this gearbox installed in the vehicle, which is actually what the goal of this one was. So we've added this pass-by noise auto post-processing thing. It is going to automatically set up an array of microphones. So these 20 microphones are kind of equivalent to having one stationary microphone as this vehicle drives by. This microphone corresponds to as the vehicle's approaching, this one in the back as the vehicle has already passed. And in that way, with a stationary mesh, we're able to evaluate what the pass-by noise would be as this car drives by. And then in PLT Viewer again, I will just start fresh. We can load the results of the simulation, and you get this automatic pass-by noise indicator, which should tell us the right side overall SPL, which we could compare to some kind of norm we're trying to fulfill or meet. Other side as well, and overall radiated power as well. In this case, let's take a look at how the right and left side differ. So there's pretty big difference between the right and left side. It's probably just due to the fact that this car is asymmetrical. We have only this gearbox radiating on one, well, not on one side, but it's more on one side. And we already saw from the directivity that it radiates more efficiently this way than that way. So all these factors could lead to having a different pass-by noise on one side compared to the other. Okay, I want to leave some part of this call to be interactive with a little bit of Q&A. I think that we've seen a little bit what the software does, how it works. Do you want to have an open discussion about the sort of acoustic problems maybe you would be interested in studying, or do you have specific questions about anything I showed?
Sorry, can you just go over how you, or what results you used from the structural analysis to input into Actran?
Yeah, sure. So in this case, the structure results, I will hide everything except this BC mesh. It is referring to displacement that is on this structure NFF. So if I right-click this and I load the structure mesh, I should be able to, underneath this coupling surface, have, again, this structure mesh, which if I look at the results, contains the solid displacement for each of these nodes.
Sorry, was that from a frequency response analysis?
Yeah, so this was coming from Solve 111 in Nastran, but it could be coming from another source as well. Could be solved by, well, here we can just see what sort of formats are supported. Could be coming from Abaqus, could be coming from ANSYS, could be coming from, yeah.
Okay, so you basically had an input of your rotational speed or something in the frequency response, and then you export that result into here.
Exactly. So this is a previous simulation that I didn't do that was already done. And that's really how this particular sort of workflow I showed today works. You start from a vibration, and that vibration can be a previous simulation, but it can also be, I would say, measurement. How can we do it with measurement? We have an option here, which is called sampled points. How does this work? With this sampled points method, we would define a number of accelerometers typically that you can define as a simple mesh with, I don't know, typically 64 points in space. And then you have a cloud of points around this coupling surface where you have the acceleration measured. And then we will project this acceleration to this coupling surface and then radiate it in the same way. The limiting point there is that the measurement will typically be much lower resolution. So when I look at this structure, we see that, okay, we have whatever resolution we have here, we have however many nodes defining this particular piece, and we have one result per node. With the measurement, typically we only have 64 is the typical maximum number of measurements. If you, let's say, just have a number of accelerometers hooked up to a collection tool. So instead of however many nodes we have here, we would have only 64 points to characterize the vibration of this structure. For low frequencies, it can be more than enough, but for higher frequencies, I think it would be better to use either another simulation or some kind of scanning measurement tool that is able to scan many different points along the vibrating structure.
Thank you. Yeah, that's perfect. Thanks.
Any other questions about what we see today or about the software and other applications of the software?
Joseph, in our environment, I don't know of many engineers who've been trained in acoustics. So where, if you're a mechanical engineer, where would you start? Because it's obviously you need a lot of background before just diving into Actran.
Yeah, so that's a good question. It really depends on what level of help you want for the sort of problems you want to solve. So there's some, I would say, online resources. If you're a Hexagon customer and have these MSC1 type licenses, there's a very nice library of learning material. If you go help, I think, I hope this link is still working the good way, but you should have access to this, what they call Nexus Academy. And by poking around here, there should be some introduction, let's say e-learning on Actran. If you, let's say, want to get a more personalized and catered training, we do offer training services. We try to price them as competitively as possible so that it is really more for us that you get to use the software. And the typical way that this works is you have to dedicate a full 3 days to it. Then an engineer like myself or one of my colleagues would follow you for the 3 days. We would have 2 days, typically, could be more or less depending on the application, where we teach you how to use the software, the different ingredients and components it has. And then on the third day, we would have from you a simplified version of something you want to model. We would show you how to set up your specific model and how to do what exactly it is you are trying to do. That's, I would say, the probably best way to become independent. But because, it takes 3 days, it's a bit of a time commitment, and we have to invoice because I would spend 3 days with you as well. These e-learning materials are free, but yeah, you have to, let's say, do the homework on your own, but they can be quite nice. We have, in addition to this, Actran Student Edition. So if you, just Google Actran Student Edition and come here, I think we have 10 or 12 workshops that are available to download immediately that are really, I would say, canonical academic sort of cases that can still be interesting. And you see that the gearbox radiation, basically what I just showed, is among these. But you have things like monopole in free field, which is something you have an analytical solution for, vibration of a plate, Kuntz tube type solution. And I think if you have no experience with acoustics, this might be a really good place to start because you can see some of these very basic cases, learn the very key components and ingredients in Actran simulation.
Right, thank you. That's a good suggestion.
Okay.
I think the other question we are asked often is, can I listen to the result?
Yes. The answer is yes. So for this one, it won't really, let's say, show anything meaningful. But what I can show, maybe let me, So where is it? Where is it? Okay, maybe I just have it here. So we have this one workshop which is shipped actually with the software. If you have it installed, this one is in the installation architecture normally. If not, I can give it to you. It's of a horn speaker. And what we can do is, so let me just give some context here. This is a simple workshop where we look at a horn. A horn is kind of a passive thing. You can think of it like a loudspeaker, or not a loudspeaker. Yeah, just like a trumpet, maybe something where if you blow in one end, you might magnify the noise that you produce at the other. And so what we can do is create a transfer function for how efficiently this horn propagates. So low frequency noise here is not efficiently radiated by this horn, but at higher frequencies it is. If this were, let's say, a complete noise file, what you can do is convert to audio, and you have some different options to fill in here, but you will end up with a wave file. So this one is not going to give anything meaningful, but we can generate an audio signal anyway. Yeah, so that is not giving anything meaningful. But what we can also do with this sort of thing is take, and I think we've maybe shown this file. So let's see, open file, wave. So if you have something like this, which is, I would say, a little bit more meaningful of a signal. So this is like the audio sort of signal you would be expecting if we, let's say, took this result at many different frequencies and had a more realistic excitation. This we could convert to audio as well. Let's see. And so this one is a song. Okay. But what we could do is we could say, okay, what about the convolution of this, which might be.
Sorry, Joseph, I think you're not sharing your audio. So maybe if you just
sorry,
stop
hold
sharing
on.
and share again.
Come here. Share includes sound. Okay, so here I was saying that this signal it's more a transfer function. It is not really going to give us a realistic sound. So if I generate the audio here, it's just making this popping sound. If we have a realistic result from a realistic excitation plus very fine frequency resolution, things like this, we can have the sound of that. And what we can do as well is a convolution. So we can say, okay, this is the recording that maybe I have with my baseline configuration. And I've done a simulation of a different configuration. And how has this changed things compared to the original? So that's what we call this convolution. We can take this, the input file would be this one here. And if I'm not mistaken, oops. Well, I did the wrong thing, but the idea is that, yeah, maybe I need to have this one be the input file. And then wait, convolution with this one. This. And indeed, you hear that it is the same signal, but maybe a little bit less low frequency content. And this workshop I can give you if you want to play around with this kind of thing. So that's how I would use this noise feature. I would, if you have a measurement, start with the measurement and then go to your simulation model, make the changes that you are thinking about implementing in the simulation model. and then use this convolution feature to see how it would change the sound that was recorded. Let's save a little bit of time. I will provide these slides to Garrett so that he can share with everyone who attended. You have my mail there. If you're interested in learning more about Actran, doing a training, figuring out how you can give it a try, or if you have some acoustic problems, go ahead and mail me. I'm happy to talk about what is possible and what you might want to give a try.